Hello everybody. In this video I want to show you how I can calculate the queuing delay in a system, in network, and I will show after that I will show you an example. Okay, let me start with a model. Let's suppose that I have a system uh, which is provide a service for me. This system has the arrival rate of lambda. Lambda requests are arrived to this system per minute per second, and after servicing, the responses would be departed from the system. Okay, I can model this system in this way. This system has a server. We showed we present the server as a circle here, and a queue. The request arrived to this system. Firstly, stand in a queue, and when the server becomes empty, they can they can enter into the server. Okay. Okay. If I want to talk about this server here and this model, I can say that, for example, a LAN, a server, or an access link can be this server in computer networks. Okay. Now I want to model this server. I said that we have an arrival rate of lambda, a waiting queue, a server with service time s, and departure. Finally, the responses will departure this server. Okay. So we said that lambda is the arrival rate, average arrival rate. It's request per second, or maybe if we are talking about a server, the arrival rate is 5 requests per second, or if we talk about LAN or links, the arrival rate is bit per second. Okay, and if I talk about the average service time S, it would be second per response, or second per file response, or second per file. If my server is a link or a LAN, the service time is L divided by R, or the transmission delay. In the course we had this equation here. We called it transmission delay. Okay, so if my server is a LAN or link, its average service time is its transmission time, L divided by R. L is the file length, and R is link bandwidth or transmission rate of the link. Okay, let's suppose that this model here is an MM1 model. Okay, here we don't want to talk about this model MM1. Okay, but we accept that our model is an MM1 model. In an MM1 model, we can say that the utilization of the server, or U, is equal to lambda times in S. What is utilization? Utilization is the portion of times, or the amount of resources in the server that we are utilizing, that we use them. For example, let's suppose that I have 10 functional unit and I'm using five, for example, 5 of them. 10 functional unit and I'm using 5 of them. Okay, in this case, my server is utilized 50% because I'm using 50% of the capacity of the server. Okay, so the utilization is bounded between 0 to 1 or 0 to 100. It depends on your needs, but I can say that this U or utilization is bounded between 0 to 1, for example. Okay, so I can say that according to this, the arrival rate should be less than or equal to 1 divided by S, because as I said, U is at most is 1. The maximum value of U is 1. So just I replace 1 instead of U, so I can say this lambda is less than or equal to 1 divided by S. What about the delay? The delay of this system or the response time of this system is equal to service time, the time that I spend in a server, plus the waiting time, the time that I spend in the queue before giving the service. Okay. The delay is equal to S divided by 1 minus U. U is the utilization here. Okay. So according to this equation, I can say that if I'm looking for the waiting time or the queuing time, simply I can say that the waiting time or the queuing delay is the delay here minus with S or the service time. So simply, if I'm talking about a LAN or a link, I can say that lambda is equal to A file per second and S is the S is equal to L divided by R. And now I can say that U is equal to lambda times in S or LA divided by R. In chapter 1, we had this equation and we called it as traffic intensity. So utilization is equal to I or traffic intensity. And if I divide the U here in the delay equation, S divided by 1 minus U, if I replace the S, if I replace the S in the delay equation with this one, I can say that the delay is equal to S divided by 1 minus U or L divided by R times in 1 minus U. Here I'm replacing the S. So we have some equations. Now let me show you an example. Let's suppose that I have a LAN which is connected to the internet. Okay, here via a link. This link has an upload rate and specific download rate. So we have two different rates, the upload rate and the download rate. Okay, so I can write those equations in the past slides in this way for upload and for download. Okay, and I know that the total delay of sending a request to the server over the internet and receiving their response, the response of those servers, uh, is a summation of delay of uplink and plus delay of downlink. But I know that mostly the amount of bits or bytes or the volume of my response is very small when I compare it with the volume or amount of bits of the response. So simply, I can say that the delay is something near to delay of downlink because because L of request, L of response is much greater than the L of request. Size of response is too much bigger than the size of request. Okay. Okay. Let's suppose that I have this uh, structure here. I have a LAN with transmission rate of 10 megabit per second. This LAN is connected to the internet via a link with bandwidth of 1.6 megabit per second, and at the other side, this router is connected to the internet, to the public internet, and the servers are on the internet. Okay, let's suppose that the systems in this LAN has 15 requests per second. So I have 15 requests per second comes from this LAN toward the internet, and their response should be returned to my LAN. Okay, I'm supposing that the request message size is 0 bit. I explained it in the past slide that we forget to upload data, the uploaded data, or the requests, my requests. Okay, so here simply I put it 0. Average size of my request is 0. Okay, but the downloaded files or downloaded requests or downloaded responses, each downloaded object has a size of 100,000 bits, and we know that the delay of internet here in the above top cloud here, the delay of internet is 2 seconds. Okay, now let me calculate the delays in this network, in this scenario. In my LAN, I know that the bandwidth of LAN, the transmission rate of LAN is 10 megabit per second. So, and my response objects have length of 100,000 bits. So simply I'm dividing L by R of LAN is the result is 10 milliseconds. So each object would receive to its final destination in just 10 milliseconds in this LAN. Okay. What about the utilization? LA divided by R is equal to 15%. So my LAN is utilized 50%. And the delay in this LAN, S divided by 1 minus R, is equal to 11.8 milliseconds. Total delay tolerated in this LAN. Okay. What about the middle link here? I can repeat my calculations. L divided by R here, R is 1.6 megabit per second. So the service time of this link is 62.5 milliseconds. The utilization of this link is about 93.75%. Wow. it means that my link here, this link here, is fully utilized. It's near to 100%. Okay, so this link is fully utilized. So let me calculate the delay of this link. If I divide 60.5 times in divided by 0.0625, 1 minus r, 1 minus u. Look at this one here. Utilization is this. I can see that the delay of this link is 1000 millisecond or 1 second. That is great. This link becomes a bottleneck here. While the delay in this LAN was only 11.8 millisecond, the delay in this link, in this bottleneck link, is 1 second. So simply, if I want to calculate the total delay, I can say that the total delay is internet delay plus access link delay plus LAN delay. So I have spent more than 3 seconds to download the responses. Okay, and what is interesting is that here this link, my access link, only serves 62.5 millisecond, but the total delay of this link is 1 second. It means that my responses should spend too much time in the queue here in the bottom. 1000 minus to 62.5 is equal to 937.5 millisecond. The responses stand in a queue for a long time. Okay, let me upgrade the access link. For example, in the past link, my access link is in the past slide. In the past scenario, in this scenario, in the first scenario, the bandwidth of my link was 1.6 megabit per second, and now I'm upgrading it to 10 megabit per second. And again, I'm trying to calculate the service time utilization and delay. I'm doing it same as before, and we can say that in the LAN the service time is 10 milliseconds. The LAN is utilized for only 50%, and the LAN delay is 11.8 milliseconds. And I can see the similar results for my access link because its transmission rate is upgraded to 10 megabit per second. So I can see similar results here. And the total delay of this scenario here, second scenario, is only 2 seconds. That is great. I'm upgrading this access link from 1.6 megabit per second to 10 megabit per second, and I can reduce the total delay about 1 second. In the first scenario, total delay was more than 3 seconds here, and now the total delay is more than 2 seconds. So I decrease the time, the delay in this case. Okay, and look at this one. The queue here, the queue in this router is very short, and look at this one here. The total delay in this router was 11.8 millisecond, and the service time of the router is 10 milliseconds. So my responses only spent 1.88 millisecond in the queue of this router. That is great. Let me show a third scenario. In the second scenario, I try to upgrade the bandwidth of the access link. But if I want to do this, I should spend lots of money. This change is costly. Okay, what can I do? Let me suppose that I have a cache network here. I'm installing a cache server in my network. And suppose that the heat rate of this cache is 0.4, or in 40% of times, this cache can respond to me. It means that in 40% of cases, these computers in my LAN can ask their request from this server. They don't need to ask this server over the internet. Okay, they just receive their responses inside my LAN. In 40% of requests will be satisfied in my LAN, and the other 60%, the other requests, should be sent over the internet to find answers. Okay. Now I'm starting to calculate the delays in the third scenario, in this scenario again. Okay, here I know that the total delay in the past scenarios I calculate the delays. Okay, so I don't want to calculate them again here. Okay, just simply I know that in 40% of cases I can receive my response right here in my LAN. So 40% of cases, the total delay is 11.8. So simply I times it, 0.4 times in 11.8 in 40% cases, because the heat rate of the network cache, my cache server, is 40%. Okay, but in 60% I have to ask from the servers over the internet. So in 60% I should go to internet, spending 2 seconds over the internet, and spending 143 seconds in the access link, and spending 11.8 milliseconds in the LAN. So the total delay would be something about 1.3 seconds. Maybe someone asks me, okay, how you calculate this, the delay of this link, this access link? It's simple. In the first scenario, as I calculate, the link here was utilized about 93.75%. And now, again, I'm using the primary link, 1.6 megabit per second. So I can use the similar calculations. But now I know that only 60% of requests would arrive and pass over this link. So simply, I'm timesing the primary utilization by 60% or 0.6. And now I can say that the utilization of the link would decrease to 56.25%. Why? Because I remove 40% of those requests and responses. Okay, so the utilization of my access link decreases to this value, and now I can simply I can calculate the delay of this link using the basic formula, and the delay is 143 milliseconds. So simply I use this calculation to show how this network cache can help me to reduce the delay times in my network. But here, what is important is this value, this hit rate value. And in this case, just I'm adding a cache server to my network. I don't change my access link because it's costly. Just I'm adding this cache server. But what is important is this hit rate. I'm repeating, this hit rate is important. If I want to be success in this scenario, this hit rate is important for me. A lower hit rate value cannot help me in this way. Okay, the last slide is an assignment for you, but it's in Farsi. I will translate it. Into English, and you have 1 week time to answer the assignment. Okay, thank you.